Here we'll work through an example where we calculate a definite integral using the definition that a definite integral equals the limit of a Riemann sum. In order to calculate definite integrals using this definition, we first need to review some properties of summations. The following three equations give formulas for the sums of powers of positive integers, and these are often very useful when we're calculating the limit of Riemann sums. The first tells us the sum of I when I goes from 1 to n. The second tells us the sum of I squared when I goes from 1 to n. And the third tells us the sum of I cubed when I goes from 1 to n. It's also very helpful to have these formulas 8 through 11 when we're trying to simplify Riemann sums. Equation 8 says that the sum of any constant c when I goes from 1 to n is just n times c. Equation 9 says that if we have the summation of a constant c times a sub I, then we can take the constant outside the summation sign. Equation 10 says that if we're looking at the summation of ai plus bi, then we can split this into two separate sums, the sum of aa plus the sum of bi. And 11 says the same kind of thing but for differences. If we have the sum of the difference of ai minus bi, then we can split that into the sum of ai minus the sum of bi. So let's now use these to work through example 5.2.2 of the textbook. This example has two parts. First, we want to evaluate the Riemann sum of the function x cubed minus 6x, taking the sample points to be the right endpoints and the interval to be from 0 to 3. And then in part B, we're asked to actually calculate the definite integral, which of course is the limit of a Riemann sum. So let's first work through part A. When there are n approximating rectangles, we can calculate the width of each rectangle using our formula. The width of each rectangle, delta x, is just the upper value of the interval minus the lower value of the interval, b minus a, divided by the number of rectangles. So in this case, that's 3 minus 0 divided by 6, which gives us 1/2. So each rectangle will have a width of 1/2. Now we're asked to use the right-hand endpoint, so we need to compute what the values of x are for the right-hand endpoints of each of these 6 intervals. And we can do that with the aid of this figure here. We can see that because the intervals have width 1/2, the right-hand endpoint of the first interval is 0.5. The right-hand endpoint of the second interval is 1.0. The right-hand endpoint of the third is 1.5, and so on. 2.0 and 2.5. So that gives us these values x1 through x6 shown here. Now we need to compute the Riemann sum for these 6 approximating rectangles. That's just the sum as I goes from 1 to 6 of the function f of x evaluated at the right-hand endpoints xi times the width of each rectangle. Expanding that out, we have f evaluated at 0.5 times delta x plus f evaluated at 1 times delta x plus f evaluated at 1.5 times delta x plus f evaluated at 2 times delta x, and so on. Substituting 0.5 into our function, remember our function is x cubed minus 6x. So substituting our value of 0.5 into that function, we get minus 2.875. And delta x is 1/2. Substituting 1 into our function, we get minus 5. Substituting 1.5 into our function, we get minus 5.625. Substituting 2 in, we get minus 4. Substituting 2.5 in, we get 0.625. And substituting 3 in, we get 9. Each of these, of course, is multiplied by delta x, which in this case equals 1/2. And so computing that quantity gives us a total of minus 3.9375. The other thing to note is that because this function is sometimes positive and sometimes negative, the Riemann sum doesn't represent the sum of the areas of the rectangles. But it does represent the sum of the areas of the blue rectangles in this figure, so those above the x-axis, minus the sum of the area of the gold rectangles, in other words, those below the x-axis. Now part B asks us to calculate the definite integral of the function x cubed minus 6x from 0 to 3. And so the way we're going to do that is using the definition. It's the limit of a Riemann sum as the number of approximating rectangles n goes to infinity. So the first thing we need to do is write out the general expression for the Riemann sum when the number of approximating rectangles is n. In this case, we can compute the width of each rectangle again. Delta x is b minus a over n, and of course b is 3 and a is 0, so we get delta x equal to 3 over n. And then we need to compute the right-hand endpoints of each of the rectangles. x0 we don't actually need, so let's scratch that out here. So the right-hand endpoint of the first rectangle, x1, is just 3 over n. The right-hand endpoint of the second rectangle is just 3 over n plus 3 over n, which is 6 over n. The right-hand endpoint of the third rectangle is 9 over n, and so on. So in general, the right-hand endpoint of the ith rectangle is 3I over n. Now, since we're using right endpoints, we can use Theorem 4 that we talked about in the previous video. The definite integral of the function x cubed minus 6x from x equals 0 to x equals 3 is the limit of the Riemann sum as n goes to infinity. So we just need to substitute in our quantities for the Riemann sum here. The function f evaluated at xi, well, xi is the right-hand endpoint, and we've just figured out that xi is 3I over n. So we can substitute that in for xi, and we have the limit as n goes to infinity of this sum of f evaluated at 3I over n. And we can substitute in for delta x, which we've computed above to be 3 over n. Now we can begin to simplify. Remember, this function here is f of x. So we simply need to evaluate that at 3I over n. So we get 3I over n cubed minus 6 times 3I over n for our function f evaluated at 3I over n. And because this quantity for delta x, 3 over n here, doesn't depend on I, we can take that outside the summation sign. That's essentially using equation 9, where the constant in this case is 3 over n. So in other words, going back to these rules, we were using equation 9 here, where the constant c is 3 over n, and we can take it outside of the summation sign. Now we can proceed to simplify this even further. First thing we're going to do is expand out that cube. So we're going to have 3 cubed times I cubed over n cubed. And then we're going to have minus 6 times 3I over n. Well, that works out to 27 times I cubed over n cubed minus 16 times I over n. And then we're going to further use equations 11 and 9 to make this even simpler. So going back, equation 11 tells us that if we have the sum of a difference, then that can be simplified as the difference of sums. And equation 9 we've used before. So we take this sum of differences in this line here, and we split it into the difference of sums. At this stage, now you can see that we have the sum of I cubed as I goes from 1 to n, and we have the sum of I as I goes from 1 to n. And again, going back to these formulas, we can then make use of formula 5 and formula 7, which tells us how to simplify these two different summations. Substituting those in, we get this third line here, where we've now made use of equations 7 and 5. And finally, we can simplify this a little bit further to get this last line here. And you should take a moment to convince yourself that these two lines are equivalent. Work through what exactly it is that we've done in moving from this line to this line in order to make things simple. Remember, the goal of this simplification is to try and figure out ultimately what this limit is as n goes to infinity, and so we want to write this in a form that makes that as transparent as possible. In this final line, we can see now that that limit is pretty easy to compute. The limit as n goes to infinity, well, what's going to happen is this quantity here is going to go to 0, and this quantity here is going to go to 0. And so we're going to be left with 81 over 4 minus 27 in the limit. So we get 81 over 4 minus 27, and we can simplify that further to minus 27 over 4, which has a decimal expansion of minus 6.75. And again, remember that the integral can't be interpreted as an area because f takes on both positive and negative values, but it can be interpreted as the difference of the areas a1 and a2, where a1 and a2 are shown in the figure here. So the definite integral x cubed minus 6x from 0 to 3 can be interpreted as area a1 minus area a2, and that works out to a value of minus 6.75. Finally, just to illustrate how these ideas of definite integrals and Riemann sums and the limit of Riemann sums are connected to one another, this figure illustrates the calculation by showing the positive and negative terms of the Riemann sum when the number of approximating rectangles is 40. Furthermore, in this table, we can see the values of the Riemann sums as they approach the exact value of the definite integral minus 6.75 as n gets larger and larger.